Hello everyone, welcome to NPTEL online certification course on fundamentals of food process engineering. We are discussing now heat exchanger. Okay. So, we have already covered few topics including the definition, types of heat exchanger, then we have discussed the analysis of heat exchanger. In the analysis we have discussed log mean temperature difference LMTD for both parallel flow and counter flow. So, if you remember the log mean temperature difference, we generally express this as theta m or delta T m, or some book you may find this as delta T Lm. So, its value is theta 2 minus theta 1 by ln of theta 2 by theta 1, right. And you just have to remember that what will be the value of theta 1 and theta 2, because if it is the parallel flow, okay. So, across the area, if you are drawing the temperature profile of both the fluid, hot and cold. So, theta 1 will be this one and theta 2 will be at the end, whatever gap we are getting, temperature difference we are getting. And if it is parallel flow, this is for the parallel flow, okay. And if we are discussing counter flow, then so this is the direction of the hot fluid and this is the direction of the cold fluid, and if we are getting theta 1 here and theta 2 here, okay. So, this will be TH1, TH2 and this is TC1 and this is TC2, right, where here in the first case parallel flow, this is TC1 to TC2 and this is TH1 to TH2, right. So, in the counter flow case, theta 1 will be TH1 minus TC2 and theta 2 will be TH2 minus TC1. So, this we have discussed in our previous classes on heat transfer. We have also discussed the overall heat transfer coefficient. So, if you remember the overall heat transfer coefficient, that is U, okay. So, U has been derived by this expression, that is okay. When area is same, in that case we can express this by this fashion. If it is for a plate, otherwise we need to consider the equation for a cylinder. If it is a tube, that is ln of Rho by Ri divided by 2 pi k L, where L is the length, okay, length of the tube, and Hi is the inner side heat transfer coefficient, convective heat transfer coefficient, and Ho is the outside convective heat transfer coefficient, right. Now, when we discuss the fouling factor, then with this the factors of fouling, resistance of fouling for the inside and outside, that will come. So, 1 by HSI plus 1 by HSO. So, this has been done when area is same. If area is not same, we need to consider area in this equation that we have already discussed. And then we have also discussed the correction factor, that depends on the various configuration of shell and tube heat exchanger, that is number of tube passes, and for this we have calculated the temperature temperature ratio and capacity ratio, temperature factor and capacity ratio, and from those two, using the chart, we have determined the values of correction factor. Now, today we will going to learn a very important concept in case of heat exchanger, that is effectiveness. Again we will discuss for both parallel flow and counter flow. After that, we will discuss the application of heat exchanger in food industry, that is what are the various types of heat exchanger that are commonly used, and will solve a numerical problem. Okay. So, now heat exchanger effectiveness and number of transfer units. So, effectiveness is very important. This in the general terms, if you analyze the effectiveness, that means that what is the maximum possible effect or heat transfer that we can get out of the heat exchanger. Okay. So, in this case, we need to look that what is the actual heat transfer happening and what the maximum heat transfer can be done, and the ratio of these will be termed as effectiveness. So, to determine the inlet and outlet temperatures for a particular heat exchanger, the analysis done more easily by using a method based on heat exchanger effectiveness and number of transfer unit. So, the effectiveness is defined as the ratio of actual heat transfer to the maximum possible heat transfer. So, actual heat transfer means the heat transfer from the hot fluid to the cold fluid that we are getting, that means the mCp delta T for the hot fluid or mCp delta T for the cold fluid. Okay. So, effectiveness epsilon, that is equal to actual heat transfer by maximum possible heat transfer. So, Q by Q max. Now, the actual heat transfer of heat exchanger is given by, as I said, flow rate of hot fluid mH dot, Cph specific heat of hot fluid. So, together this constitute the heat capacity of the hot fluid into temperature drop, that is Th1 minus Th2, and this heat is taken by the cold fluid. So, mass flow rate mc dot into Cpc specific heat of the cold fluid, and temperature it has increased from Tc1 to Tc2. So, Tc2 minus Tc1, this will be the value here for the change of temperature. So, this is the actual amount of heat transfer happen. Now, the maximum possible heat transfer will occur if the outlet temperature of the fluid with smaller values of heat capacity, that is either Ch or Cc, is equal to the inlet temperature of other fluid. So, it means that heat capacity, the term Ch or Cc, right. Now, okay. So, Ch or Cc, which is respectively the heat capacity of hot fluid and cold fluid. So, this is equal to mH dot into Cph, and this is equal to mc dot into Cpc, right. Now, if the flow rate of this fluid, the hot fluid, is less, or if the specific heat, that is heat required to increase per unit temperature for that particular fluid is lower. So, this will be lower, and similar is the case of cold fluid, right. So, if this is low, either Ch or Cc, that means the maximum heat transfer Th1 Ch into Th1 minus TH2 okay. So, Q is equal to CH into TH1 minus TH2 or TC2 minus TC1. So, if this is small okay, or this is small, so this difference will be very high, and if it happen, that is the maximum heat transfer happens. So, what will be there? The outlet temperature of the fluid for which the heat capacity is minimum, the outlet temperature will be inlet temperature of the other fluid. Okay. So, that is the maximum amount of heat transfer that may takes place, right. So, for example, if the if Cc, if the cold fluid heat capacity of the cold fluid is the minimum in this case, okay. So, outlet temperature of the fluid with smaller values of heat capacity. So, then it is equal to the inlet temperature of the other fluid, right. So, in that case, if this is minimum, Tc2 will be equal to Th1, and if Ch is minimum, so Th2 will be equal to Tc1. Okay. So, then we can say that Q max will be Ch into Th1 minus Tc1 or Cc into Th1 minus Tc2. This happened because Th1 minus Th2, now since Ch is minimum, so Th2 will be transferred by Tc1, the outlet will be inlet of the other fluid. So, it is Tc1 or Cc if it is minimum, then Tc2 minus Tc1. So, outlet of cold fluid will be equal to inlet of the other fluid Th1, right. So, maximum heat transfer will be this one, that is the maximum extent of transfer of heat we can achieve. Okay. So, Q max will be minimum among these two values. Okay. So, now Q max, that is C min, whatever it may be, either Ch or Cc, both the case what we are getting, that C minimum into Th1 minus Tc1. Okay. Th1 minus Tc1, here also Th1 minus Tc1, only thing either Ch is minimum or Cc is minimum, right. So, we can write Q max equal to C mean Th1 minus Tc1. So, effectiveness will be the actual transfer in case of hot fluid that we are getting, that is Ch into Th1 minus Th2 by C minimum. So, if Ch becomes minimum, in that case outlet will be Th2 will change by Tc1. So, we can write C minimum into Th1 minus Tc1. Okay. Similarly, if we consider cold fluid for finding the effectiveness, we can write actual heat transfer, that is Cc Tc2 minus Tc1 divided by C minimum Th1 minus Tc1. So, in this case Ch is minimum and in this case Cc is minimum. Okay. So, this will be effectiveness. So, heat transfer is given by the following equation, that is Q is equal to effectiveness okay. So, Q will be equal to effectiveness into C minimum into Th1 minus Tc1, because actual heat transfer is this one, okay, or this one. Okay. So, this is equal to Q, actual heat transfer, either this or this. Now, actual heat transfer will be then effectiveness into this value C minimum into Th1 minus Tc1. Now, what is number of transfer unit method? Okay. NTU method, it is very common in case of calculating the heat exchanger effectiveness. In terms of NTU, we generally calculate, and it is given in the specification of heat exchanger as well. So, heat exchanger effectiveness is a function of several variables, but it is inconvenient to combine them in a graphical form. Heat exchanger effectiveness can be expressed as a function of 3 non-dimensional parameter, which is known as NTU method. So, what are those parameters? First is NTU, the value is UA by C minimum. U is the overall heat transfer coefficient, okay, watt per meter square degree Celsius or meter square degree Kelvin. A is the area meter square by C minimum, that is m dot mass flow rate into specific heat. So, this is one parameter. The other is R capacity ratio, C minimum by C max, and then the other factor that we need to consider is flow arrangement. So, first we will see the effectiveness of parallel flow heat exchanger. Okay. So, for parallel flow heat exchanger, in the previous class we have derived this for the log mean temperature difference, that how we can relate the differential change in the temperature for a differential area, and then we have equated the change for hot and cold fluid to find the log mean temperature difference. So, here also we will do the same thing. So, just to have the idea of the heat transfer, I am drawing the profile, temperature profile. So, this is the hot fluid and this is the cold fluid, okay, and I am taking a small area dA. So, this is TH1, TC1, TH2, TC2, okay, and this one is DTH, DTC, right. So, heat is coming from the hot fluid to the cold fluid. The heat exchange dQ through the area dA, okay. Okay. So, heat exchange, that will be U into dA into TH minus TC. So, U is the overall heat transfer coefficient, as I mentioned that there will be a surface through which these two fluids are exchanging heat, because always heat exchange happens through through a surface in case of heat exchanger. So, overall heat transfer coefficient U based on the conductivity of the surface and both the side hot fluid and cold fluid side convective heat transfer coefficient or fouling, whatever may be there, we will calculate U. We have already discussed how overall convective heat transfer coefficient can be determined, right. So, U into dA, that is the elemental area, into temperature difference between the hot and cold fluid. So, this difference is the driving force for moving dQ amount of heat through the dA amount of area from the hot fluid to the cold fluid. So, for the hot fluid we can write mH dot into Cph, specific heat, into dTH, okay, the temperature drop in the hot fluid, and we are putting minus sign because it is reducing with increasing A. That is equal to MC dot cold fluid flow rate into Cpc into dTc, okay. So, this is increasing towards increasing A. So, minus Ch into dTh, that is equal to Cc into dTc, this is equal to dQ. So, now we know that we have already seen that we need to find dTh minus dTc. So, we can write that dQ by this Ch and here dQ by Cc. So, what we will do now, see dTh equal to minus dq by Ch and dTc is dq by Cc. So, d of Th minus Tc, that is the temperature difference between the small area dA, that is equal to minus dq 1 by Ch plus 1 by Cc. Okay. So, Ch and Cc heat capacity of the hot and cold fluid respectively. So, then again this dq that we can write in this form, that is u into dA into here Th minus Tc was there, I have taken this Th minus Tc to the left side. So, d of Th minus Tc by Th minus Tc. So, the similar form like d theta by theta that we have got in the previous class. So, ln theta, that will be the term, and then we can if we integrate this, and here also dA will be integrated and the value of A will come. So, finally, the equation that we will get okay. So, after integration we are getting this equation. We are integrating from 1 to 2. Okay. So, ln of Th2 minus Tc2, Th2 minus Tc2 divided by Th1 minus Tc1, okay, and that is equal to minus Ua 1 by Ch plus 1 by Cc. So, then here what we can do is minus Ua by Ch, we can take 1 by Ch common. So, this will be 1 plus Ch by Cc, and this term left hand side we can write Th2 minus Tc2 divided by Th1 minus Tc1, that is equal to e to the power minus Ua by Ch into 1 plus Ch by Cc. Okay. So, then what we can do is we will relate it with effectiveness. Effectiveness what was? Actual heat transfer divided by the maximum possible heat transfer. So, effectiveness for the hot fluid was Ch into Th1 minus Th2 by C minimum Th1 minus Tc1, and for the cold fluid it was Cc Tc2 minus Tc1 divided by C minimum Th1 minus Tc1. Okay. So, from this equation and from this equation we need to calculate Th2 and Tc2. Okay. So, considering this one, we can write that effectiveness into C minimum Th1 minus Tc1, we can write effectiveness into C minimum Th1 minus Tc1, this is equal to Ch into Th1 minus Th2, right. So, I can take Ch this side, right, okay, and we can also write that Th2 this is equal to Th1 minus epsilon C minimum Th1 minus Tc1 divided by Ch. Okay. Similarly, if I consider this part, I can write effectiveness into C minimum into Th1 minus Tc1, this is equal to Cc Tc2 minus Tc1, okay, and here again I will take this Cc this side, okay. So, then my Tc2 will be TC1 plus effectiveness into C minimum into TH1 minus TC1 by Cc. Okay. So, very clearly you can understand that see TH2 will be the lower temperature than TH1. So, TH1 minus effectiveness into this value. Similarly, TC2 will be higher than TC1 because TC1 is going to increase to TC2. So, TC1 plus effectiveness into C minimum TH1 minus TC1 by this. So, basically this is kind of a kind of the fraction that we are achieving by the ratio of C minimum by Cc. Okay. So, if it is very close to this, so we can get effectiveness higher, right. So, because if effectiveness will be 1 in that case, C minimum will be equal to Cc and this Tc2 will be eventually Th1. So, this is how we have found out Th2 and Tc2. Now, in the in this case that we are getting Th2 minus Tc2, here we will substitute these two equation. Okay. So, from here Th2 minus Tc2, we will put these two equation to remove this value Th2 and Tc2, right. So, eliminating Th2 and Tc2 from that equation, what we are getting that we have put the values of Th2 and Tc2 in terms of the other parameter that just we have derived. So, 1 by Th1 minus Tc1, that is equal to Th1 minus Tc1 minus effectiveness into C mean Th1 minus Tc1 into 1 by Ch plus 1 by Cc. This will be the right side is same, exponential minus UA by Ch into 1 plus Ch by Cc. Now, from this we can calculate if we can take Th1 minus Tc1 common. So, this will be cancelled. So, 1 minus, okay. So, we are taking this factor Th1 minus Tc1 from here and here. So, this will be cancelled. So, 1 minus effectiveness into C minimum, okay, 1 by Ch plus 1 by Cc, this is equal to exponential of this term, right. So, effectiveness can be termed as 1 minus exponential minus UA by Ch into 1 plus Ch by Cc divided by C minimum into 1 by Ch plus 1 by Cc. Now, the thing is which one is minimal, Ch or Cc. Based on that we can define effectiveness. First case, if Cc is greater than Ch, that means Ch is our C minimum. In that case, here see what will happen, that 1 minus UA by Ch. So, Ch is C minimum now into 1 plus Ch, that is C minimum by C max divided by C minimum, okay, into Ch is minimum here. So, we take this minimum out. So, or we take this C min inside. So, we are getting 1 plus C minimum by Cc, that is C max. And the second case would be if Cc is less than Ch, that is if Cc is the minimum, then the value will be 1 minus exponential minus UA by C max into 1 plus C max by C min, because Ch by Cc. So, Ch is high now and C is the minimum, divided by 1 plus C minimum by C max, okay, because Cc is less than Ch. So, Cc is the minimum one. So, now we can write here this is minimum, okay. So, we are getting 1 plus C min by C max here. So, combining both the equation, we can get effectiveness is equal to 1 minus exponential minus UA by C mean into 1 plus C mean by C max divided by 1 plus C mean by C max. Okay. So, this is the common equation that we are getting. So, the effectiveness of parallel flow heat exchanger is given by 1 minus exponential minus U A by C mean, that is replaced by NTU, number of transfer unit, into 1 plus C mean by C max, that is the capacity ratio R, divided by 1 plus R. So, effectiveness for counter flow heat exchanger, this will be done in the similar fashion. So, the temperature of both the fluid decreases along the length of heat exchange. So, the heat flow equation is given as follows. Here because the framework will be, the configuration of system is such that temperature profile, if we draw, it will be kind of this. So, this is TH1, this is TH2 and this is TC1, TC2. So, across the small area dA. So, if we look towards the small area change, we are getting dTH, that is negative, and also if we move to this direction. So, temperature profile of the cold is also decreasing, right. So, we can write here as dQ is equal to U dA Th minus Tc minus m dot Cph dTh. So, similar fashion as we did for the earlier case. So, minus Ch into dTh, that is equal to minus Cc into dTc. So, rest of the derivation approach is similar as we did for the parallel flow. Similarly, we will just have dTh minus dTc in terms of dQ, Ch and Cc. Okay. So, the expression will come as effectiveness equal to 1 minus e to the power minus NTU into 1 minus R divided by 1 minus R, that is again capacity ratio C minimum by C max, into exponential minus NTU into 1 minus R. Okay. So, we will stop here, we will continue in the next class. Thank you.